Welcome to The Explainer. Today, we're going to pull back the curtain on the elegant, secret rules that govern the absolute rock star of the periodic table, the element of life itself, carbon.
So, let's just jump right in with a big question. Have you ever wondered why this one single element gets a whole branch of chemistry named after it? What makes carbon that special?
Well, the short answer is this. Carbon is basically life's master architect. It has this incredible, unique talent for building the massive, complex backbones of millions of different compounds. And here's the kicker. It does it all by following just a few surprisingly simple rules.
All right, so let's start with the basics, the building blocks themselves. We're going to look at what I like to call carbon's two main superpowers. It really just boils down to these two things. First up, you've got catenation. It's a fancy word, but all it means is that carbon is amazing at linking up with itself to form these long, superstable chains. Think of it like cosmic Legos. And second, there's tetravalency, which means it can form 4 really strong bonds with other atoms. That's it. These two simple properties are the reason organic chemistry is so incredibly vast and diverse.
Now, with millions of possible structures, you can probably imagine that drawing every single atom and bond would be a complete nightmare, right? So chemists needed a shortcut, a way to sketch out the blueprints for these molecules without all the clutter.
And you can literally see that evolution right here. We start with the complete structural formula. Yeah, it shows everything, but wow, is it messy. Then you get the condensed formula, which cleans it up a bit. But the real game changer, the one chemists use all the time, is the bond line formula. It's pure elegance. Every corner or end point is a carbon, and you just assume the hydrogens are there. It's clean, it's simple, and it's incredibly powerful.
You know, this clear understanding we have now wasn't always the case. For a really long time, scientists were convinced that these complex organic molecules could only be made by living things, and it was all because of one very popular and, well, wrong theory. And that theory was called the vital force theory. The idea, pushed by the famous chemist Berzelius, was pretty straightforward. Organic compounds had some kind of mysterious spark of life, a vital force that came from living things, and there was no way we mere mortals could ever recreate that spark in a lab.
But then, 1828 happens. A German scientist, Friedrich Wöhler, is in his lab. He's not trying to disprove anything big. He's just trying to make a boring, inorganic compound. But in the process, the atoms in his mixture did a little shuffle, and he accidentally created urea, a famous organic compound found in urine. It was the first time ever that an organic molecule was made from totally non-living stuff.
With that one single accidental experiment, the whole paradigm just shattered. As the Hindi saying goes, the time changed, the situation changed, the feelings changed. The vital force was dead. And just like that, organic chemistry became a real science, a science with rules we could actually understand and, crucially, use ourselves.
Okay, so this discovery blows the doors wide open, but it leads to a huge new question. If there's no magic life force making things happen, then how do these incredibly strong chemical bonds actually break apart and form new ones during a reaction?
This is really the heart of it, right? You've got these covalent bonds, which are basically pairs of electrons playing tug-of-war to hold atoms together. So how on earth do you get them to let go?
Well, it turns out there are really 2 main ways it can go down. The first is called homolytic fission. Think of this as a fair, symmetrical split. The bond breaks and each atom walks away with 1 electron. This creates these neutral but super reactive things called free radicals. Or you can have heterolytic fission, which is an unfair, unsymmetrical split. One atom gets greedy and snags both electrons, leaving the other with nothing. This creates charged particles, positive carbocations and negative carbanions. And right here, these are the key players on the field, the so-called reaction intermediates. They don't stick around for long, but they are the absolute stars of the show. You have the carbocation, a carbon that's missing electrons, so it's got a positive charge, the carbanion, which has extra electrons and a negative charge, and the free radical, which is neutral but has this lonely, unpaired electron that makes it desperately want to react.
So what makes these molecules tick? What decides how they're going to react? Well, it all comes down to a constant, invisible tug-of-war for electrons that's happening inside the molecule all the time. That's not an exaggeration. The entire personality of a molecule, how it behaves, how it reacts, is all dictated by these permanent pushes and pulls on the electrons within its structure. We call them electron displacement effects.
And there are 2 big ones to know about. First is the inductive effect.
This is a push or a pull that travels through the single bonds of the molecule. You can think of it like a ripple in a pond. It's strongest right next to the source and gets weaker the farther away you go. Then you have the resonance effect. This one is a total team effort. It involves sharing electrons over a whole group of atoms, which makes it a much stronger, more widespread effect.
Okay. So we've talked about building blocks, the key players in reactions, and these invisible forces, but let's be real. Why does any of this actually matter? What's the big payoff for knowing all this stuff?
The point is, understanding these forces gives us a kind of superpower. It gives us the ability to predict how a chemical reaction is going to play out before it even happens. Let's go back to our friend the carbocation. Remember, it's that carbon with a positive charge. It's unhappy because it's missing electrons. So its stability depends entirely on its neighbors. If it's surrounded by groups that can gently push some electron density its way, it helps to spread out and neutralize that positive charge, making the whole thing way more stable.
And you can see that exact principle right here on this chart. A primary carbocation is only attached to one other carbon group, so it gets barely any help. It's pretty unstable. A secondary one has two neighbors helping out, so it's better. But look at the tertiary carbocation. It's the king of stability because it has three helpful neighbors all donating a bit of electron density to stabilize that positive charge.
And this, right here, is the ultimate goal. This is the payoff. By understanding these invisible forces, we can just look at a molecule's blueprint and predict how it's going to behave. We can see which parts are stable, which parts are going to react. It's almost like learning to read the molecule's mind.
So from carbon's simple superpowers to predicting the complex dance of its reactions, you can see that chemistry is really just a science built on a foundation of elegant and incredibly powerful rules. And that really leaves you with one final big thought. If a few simple patterns can explain the behavior of millions of compounds, what other complex systems out there are just waiting for us to find their secret rules?